Let's talk about complex numbers. All of this should be review from Algebra 2, or I guess new. If you're in Algebra 2, maybe Algebra 1. Let's review. First thing to remember is in that pink box that I equals the square root of -1. I is a basic imaginary number equal to the square root of -1. So we can see from that if I equals the square root of -1 that I squared equals -1. When we're dealing with complex numbers, obviously we're going to be dealing with I. The general form of a complex number is right here, A plus BI. A and B are real numbers. We call A the real part and B the imaginary part. So the first part of remembering about complex numbers is easy. Let's look at these examples. In the first one, what's the real part? What's the imaginary part? 3 is the real part. 4 is the imaginary part. Try these other ones. Pause if you want to answer before I do. The last two are the only ones that are really tricky. The real part of 6i is 0, the imaginary part is 6. The real part of -8 is -8, and the imaginary part is 0. When we have that 6i, when it's just an imaginary part, we call that a pure imaginary number. A regular, real number like -8, you could think of that as an imaginary or a complex number with an imaginary part of 0, but that probably would only be helpful to you if you're adding and subtracting imaginary numbers or complex numbers with regular numbers. The important thing that you need to remember, though, when we're adding and subtracting, and that's next, is that I is not a variable. We can treat things like AI and BI as like terms, but it'd be in the same way that we treat 4pi and 3pi as like terms. Pi is not a variable, neither is I. So let's talk about adding and subtracting. You can see that's pretty easy. A plus BI, there's one complex number, plus another complex number, equals the real parts added together, plus the imaginary parts added together, times I. I is with the imaginary parts. You see how it was like BI plus DI is B plus D times I. Let's try this first example down here just to make sure that we've got it. 3 plus 5i plus 4 minus 2i is 3 plus 4 plus 5 minus 2, or 5 plus -2, I. You could skip this step if you want to, if you do that part in your head, and your answer is 7 plus 3i. Easy enough. We'll come do some more in a minute. When we multiply A plus BI times C plus DI, we're basically multiplying just like we'd multiply any other binomial, or a set of binomials. Or even if it's a monomial, and a binomial use distributive property. Or the FOIL method, whatever you call it, multiply like you're multiplying two binomials. So let's try that. Well, let's finish out this general form here. A times C is AC. A times DI is plus ADI. BI times C is plus CBI, and then BI times DI is going to be plus BDI squared. So simplify this a little bit. AC, what I want to remember now is that when we see I squared, highlight it for you, when you see I squared, you think -1 right away. So this BDI squared is BD times -1, or minus BD. So AC minus BD plus ADI plus CBI could be seen as AD plus CBI. You could write it that way, or you could leave it expanded out without factoring out the I from those two terms. But the important thing to remember in this one is that I squared equals -1, so that makes that minus BD. Let's try these examples below. Pause now if you want to try them and then see the answers. Here's the answers to the number 2 and number 3. Notice how much nicer the multiplication works out when we've got real numbers. And the only tricky thing about number 2 is that you got to remember this negative here distributes to everything in the parentheses. So 3 minus 4 is -1, 5i minus -2i is 7i. Now, when we're thinking of I to any power, I want to look at this one especially. You need to think about changing this to an even power, because I to an even power is -1, if that makes sense. So I to the 23rd power is really I to the 22nd plus 1. And now's when we got to remember exponent rules. If you've got exponents added, that means you multiplied, or that you could see this as multiplying I to the 22nd times I to the 1st. I to an even power is going to be -1. So let's make that -1 times I to the 1st, which is -I. See how easy that is? So you just want to try to convert it to an even power times I to another power, and that's the way you figure out those kind of problems. The next important thing about complex numbers is the complex conjugate. Basically, the complex conjugate of a complex number like a plus bi, so that'll be my first number, its conjugate, its complex conjugate, is a minus bi. Easy enough, just change the plus to minus. If it's a minus, change it to a plus. So what we're doing, this is another thing where we're making a difference of squares. So if we wanted to simplify this division, or simplify this rational expression made of complex numbers, we'd multiply by the complex conjugate of the bottom, c minus di over c minus di. Now what we're doing, look at the bottom there in the denominator. We're creating a difference of squares. It looks like a factored out difference of perfect squares. On the top, we're just going to let it chill out. So I got a plus bi on the top times c minus di. If these are real numbers, we'd simplify it more, but they're just constants represented by those letters, so it doesn't make sense to really mess around with it. But look at the bottom. C plus di times c minus di is going to be c squared minus di squared. Let's just look at this piece by itself. If you simplify just that piece, again, leaving the numerator the same, you get c squared, and then d squared is just d squared, but I squared is -1. So you get c squared minus negative d squared, or c squared plus d squared on the bottom. So you can almost automatically, or you should be able to automatically go from this to this without much trouble at all. It's just making your own difference of perfect squares. It's just like rationalizing the denominator of a complex expression. Try these two below. If you want to pause now, the answers will be up in a minute, so try them yourself and then press play. Let's check out these answers. You can skip the explanation if you want to, fast forward a bit. In this one, the only tricky part, I think, remember right here, we went from c plus di times c minus di to c squared plus d squared. So here we got 1 minus 2i times 1 plus 2i, so that should go to 1 squared plus 2 squared, 1 plus 4. You can multiply it out if you want to, and I did that in the next thing so you could see a little bit better in number 2. In the top part, we just FOIL out 3 plus 5i times 1 plus 2i, or do distributive property, whatever you call multiplying binomials. Multiply those binomials. 3 plus 11i plus 10i squared is the same as 3 plus 11i Remember, I squared is negative 1, so that's minus 10. 3 minus 10 is negative 7, plus 11i, all over 5. Look at number 2. We're multiplying by the complex conjugate. I have 4 minus 3i times 4 plus 3i, which equals 4 squared, 16, minus 3i squared, which you find out is 9. So see how it's 4 squared, 16, plus 3 squared, 9. C squared plus d squared. It works that way every time. You're doing that on purpose. That's why we multiply by the conjugate. And on top I've got 100. I distributed the 25. 100 plus 75i. 100 plus 75i over 16 plus 9 is, move on up here, 100 plus 75i over 25. And then we can simplify a bit because 25 goes into 100 4 times, into 75 3 times, and into itself once. Only simplify like that if it goes into everything. So then I have 4 plus 3i. Here's a couple of other things to remember about complex numbers. Go ahead and write this in your notes. The square root of a negative number is I times the square root of that number, or really plus or minus. This first number here, this first one here, the positive one, we call the primary square root, or the principal square root. And then this other one is the other square root. You know, when you take a square root, when you're solving, you end up with a plus or minus. So the principal square root, if they ask for that, is just the positive one. And this comes in handy when you're solving equations. Some equations have complex solutions, like x squared plus 9. Subtract the 9 to the other side, and x is plus or minus 3i, or plus or minus the square root of negative 9. So we can assume from that some functions have complex roots or zeros, and usually those come when the quadratic formula, or when the discriminant, this little piece of the quadratic formula, is negative, less than 0. So those are just some things to remember as we work with these complex numbers.